All right, let's dive into a question that's, absolutely fundamental to farming and really our planet's future. How do you figure out exactly how thirsty a plant is? It sounds simple, right? But getting it right is this incredibly fascinating science.
For anyone who's ever tried to grow anything, this is the ultimate balancing act. Too much water? That can be just as bad as not enough. You get waste, you get disease, you get really disappointing crops. The real challenge is finding that sweet spot, that perfect, precise amount.
And of course, scientists have a name for this perfect amount, the crop water requirement, or CWR. The easiest way to think about it is like an ideal hydration plan for a plant. It's everything it needs to live its best life and reach its full potential without ever getting stressed out about being thirsty. So, to solve this whole puzzle, we're going to follow a pretty clear roadmap. First, we'll nail down what a plant's thirst actually is, scientifically speaking. Then, we'll hunt down three key clues: the atmosphere, the crop itself, and the soil. And finally, we'll see how all these pieces click together to give us the answer we're looking for. So our investigation kicks off with this really crucial concept, the scientific way to measure a plant's total water loss. Its thirst, really, is called evapotranspiration. It's kind of a two-for-one deal, combining evaporation from the soil surface with transpiration, which is the water vapor the plant breathes out from its leaves. Okay, so here's the bottom line. The crop water requirement is the water we need to add. Crop evapotranspiration is the water the whole system loses. But, and this is the important part, for our calculations, they're basically two sides of the same coin. The numbers are the same because we have to figure out the loss to know how much to apply. Let's get to our first big clue. Before we can even think about a specific plant, we have to understand how much water the environment itself is demanding. We literally have to learn how to read the atmosphere. The Food and Agricultural Organization, the FAO, gives us the standardized three-step process. First, we figure out a baseline for the atmosphere's thirst, called ETO. Then, we tweak that for the specific crop we're dealing with using a factor called Kc. And finally, we get real and account for the actual soil conditions with one last factor, called Ks. So what on earth is ETO? Well, think of it as a universal yardstick for how thirsty the air is on any given day. It's a measurement of the potential water loss from a totally standardized hypothetical surface. Imagine an endless field of perfect, well-watered grass. This gives us a baseline that works anywhere in the world, no matter what crop you're growing. And what's driving this atmospheric thirst? Four key things which we can get from any modern weather station. The sun's radiation and higher temperatures. That's the energy that powers evaporation. Super low humidity means the air is just ready to soak up more water. And a good breeze, well, that just whisks all that moisture away even faster. Now, to calculate ETO, scientists have a gold standard, the FAO Penman-Monteith equation. It's a really complex formula, but what it's basically doing is modeling the physics of how energy and water vapor move around. It's recognized as the single most accurate way to get that baseline reading of the atmosphere's thirst. Okay, so we've got our baseline from the atmosphere, the ETO, but a field of corn is obviously very different from a field of grass. So our next job is to adjust that baseline for the unique personality of the crop we're actually trying to grow. This is where the crop's unique code comes into play. We do this with a really simple but powerful bit of math. We just take our reference ETO and multiply it by something called the crop coefficient, or Kc. That simple step gives us the potential water need for our specific crop, assuming it has all the water it could ever want. So this gets to the why behind KMC. A tall corn stalk is going to catch the wind way differently than short grass. A dark leafy vegetable absorbs more sunlight, that's called albedo. The shape of its leaves affects how easily water vapor escapes. And of course, how much ground it covers changes how much water evaporates from the soil below. The KMC value just bundles all those differences into one handy number. And this also shows that a crop's thirst changes like crazy as it grows. That K value isn't static. It's really low when the plant is just a tiny seedling. It shoots up as it grows, it peaks during that lush mid-season, and then it drops back down as it gets ready for harvest. Okay, so far we have the atmosphere's demand and the crop's unique needs. But we've kind of been living in a perfect world where water is unlimited. Now it's time to get real and bring in our final variable: how much water is actually in the soil. Because in the real world, soil dries out. Water isn't always just sitting there, perfectly available for the plant's roots to slurp up. This creates stress, and we absolutely need a way to factor that into our equation.
You know, when soil is nice and wet, water is easy for the roots to absorb. But as that soil gets drier, the water that's left is held onto much more tightly by the soil particles. The plant has to work way harder to pull it out. And when it just can't pull water fast enough to keep up, it starts to experience water stress. A good way to think about it is that the water in the soil is in two zones. First, there's the readily available water, or raw. That's the easy-to-drink portion. A plant can use all of that water without breaking a sweat. But once that's gone, it has to start working a whole lot harder for every drop. And this is where our final factor, the water stress coefficient, or Ks, comes in. As long as the plant is happily sipping on that readily available water, Ks is just equal to 1, and it doesn't change our calculation at all. But the second the soil moisture dips below that easy-to-drink threshold, Ks becomes a number less than 1, and it reduces our calculated water use to reflect the plant's real stressed-out condition. So, we've done it. We've gathered all our clues. The atmospheric demand, ETO, the crop's unique code, Kc, and the soil stress factor, Ks. Now, it's time to put it all together and finally crack this case.
And here it is, the final formula. The adjusted real-world crop water need is our atmospheric baseline, ETO, times the crop coefficient, Kc, times the water stress coefficient, Ks. This simple multiplication gives us the most accurate picture of what a plant is actually using day to day.
Let's look at this in action with a quick example for tomatoes. Just check out July. The atmospheric demand, ETO, is high, 4.52 millimeters a day. The tomato plant is in its peak growth stage, so its Kc is also high, over 1. This means its potential water need is almost 5.3 millimeters every single day. Once we subtract what it got from the rain, we see it needs almost 57 millimeters of irrigation that month to really thrive.
And that is the whole point of this. We scientifically figure out the total water the crop needs. We subtract what nature gave it for free through rainfall, and that difference is the exact amount we need to add through irrigation. No more guesswork, no more just hoping for the best.
Look, this isn't just some academic exercise. This science gives us the power to use one of our most precious resources, water, with incredible precision. It's a critical tool for growing more food with less water. And that leaves us with one final massive question. Now that we can calculate a plant's exact thirst, how are we going to use this knowledge to reshape agriculture for a much, much drier world?